Hi everyone, and welcome to the Microsoft Research Forum. Today, we're bringing you our March 2026 episode. I'm Anson Ho, a Senior Program Manager here at Microsoft Research Redmond, and I'm excited to be hosting today's episode with you. At Microsoft Research, we are lucky to work on problems driven by curiosity. Big, open questions that often start as ideas on a whiteboard and grow into breakthroughs, tools, and real-world impact. Microsoft Research Forum is where we bring that journey together. Today's lineup really shows the range of work happening across MSR. From foundational research on how AI agents interact, to open source systems that are already being used at scale and brand new capabilities. Let's dive in. As AI agents become more capable, they are no longer working alone. Agents start interacting with each other in shared environments. And when that happens, things can get interesting. Here in Redmond, Gagan Bansal from MSR AI Frontiers studies what happens when agents start transacting in market-like settings. Using an open source environment called Magentic Marketplace, his team explores how agents behave when incentives don't perfectly line up and what kind of failure modes start to appear as systems scale. This is exactly the kind of early curiosity-driven research that helps us understand what could go wrong before these systems light up. Take it away.
Hi, I'm Gagan Bansal, and I'm a researcher at Microsoft. And today, I want to talk to you about our recent work on applying societies of agents in markets. And although I'm presenting, this work was a collaboration between many amazing colleagues across Microsoft. Capabilities of AI agents are improving rapidly. We're quickly moving towards a future where each one of us will have personal agents. Now, in a world where everyone has agents, we believe societies of agents will drive new applications where our agents will have to interact with other agents. But how can we trust agents that we don't control, or agents that might know things ours doesn't, or even have competing goals? At Microsoft, we've been building on our expertise in multi-agent frameworks like Autogen and Magentic One to create useful societies of agents, ones that add value, save time, and don't cause harm. To enable this future, we need to understand how agents behave when they interact at scale. Recent examples from the open source community, where agents could talk freely on the forums, only underscores how timely and important this question is. Let me show you what we built and what we found. Imagine a marketplace where all the buying and selling is done by agents representing people. We call these settings as two-sided agentic markets. This setting is a great testbed for societies of agents because every agent has access to different information and competing incentives. To systematically study two-sided markets, we at Microsoft Research built a new simulation environment called Magentic Marketplace. Here, assistant agents represent customers, service agents represent businesses, and a marketplace sits in the middle, handles search, communication, and transaction between agents. Here's a typical interaction. Suppose a customer wants to find a restaurant with something specific, like delicious empanadas and outdoor seating. The assistant can search the marketplace, talk to the service agents, ask about menus, check amenities, and finally make a reservation. This framework allows us to test hundreds of agents buying and selling in parallel. We used it to systematically ask many research questions. Do these agents even add value for customers and businesses? Does the quality of search result impact their behavior? Are they vulnerable to any biases or manipulation? We built this framework as a general research tool. It can be used to ask many other questions, even for domains beyond markets. We started by asking whether agents actually add value for consumers. To find out, we implemented agents using frontier and open source models and computed the welfare that they achieve. Here, welfare is the value customers get from their purchase minus the price they paid. Higher is better. We observed that when agents have access to high-quality search results, frontier models like GPT-5 and Sonnet 4 reached near optimal welfare. They talked to business agents, gathered missing information, and made good choices. But we found that agent performance was tied to the quality of search results. When the search quality dropped, performance dropped. We also observed that there's still a large gap between the welfare achieved by frontier models and open source models. In addition to the impact of the quality of search results, we also wanted to test whether the number of search results impact welfare. So we gave agents more search results, varying them from 3 to 100, and expected the welfare to increase. But the opposite happened, resulting in a surprising paradox of choice. Welfare dropped for almost every model. This happened because agents didn't explore enough and contacted few businesses. We also conducted experiments that tested whether the order of offers from service agents matters. It did dramatically. Almost 80 to 100% of the agents accepted the first proposal they received. They never even looked at the alternatives. Think about what this means for a real market. Speed beats quality. A business gains more from responding fast than from offering a better deal. That's not a healthy dynamic. We also tested vulnerability to fake reviews, fake awards, and prompt injection. Some frontier models resisted everything, but others were completely compromised. All payments were redirected to the attackers. These are early findings, and markets are just the beginning. Societies of agents will emerge anywhere agents represent people with different interests, such as supply chains, hiring, and negotiation. Magentic Marketplace is open source on GitHub for the community to run experiments, stress test agents, and help answer the harder questions. What guardrails do we need? How should markets be designed when both sides are AI? What we've shown is that simulation matters. Agents can add value, but they also inherit biases, fall for manipulation, and make choices that reward speed over quality. These are not edge cases. These are behaviors that only emerge when societies of agents are tested at scale. If these agents are going to take high-stakes decisions on our behalf, such as making transactions to other agents, we should understand their behaviors and biases before deployment, and not after. Please check out our papers and GitHub repository for more information, and thank you for attending the Microsoft Research Forum.
Thanks, Gagan. I love this work because it reminds us that as agents get more powerful, we have to think beyond individual performance and really understand system-level behavior. And from there, it's a great segue into work that takes these ideas and starts building systems that can actually learn and adapt over time. Learning from experience is something humans do naturally, but for AI agents, it's often bolted on as an afterthought. Joining us from MSR Asia in Shanghai, Luna will introduce Agent Lightning, an open source framework that makes learning a first-class capability for agents. With minimal code changes, agents can improve over time using reinforcement learning and related methods. This project has taken off quickly in the community and is a great example of MSR research scaling through open source and shaping how people build agentic systems in practice. Luna, over to you.
Hello from Shanghai. I'm Luna Chiu, Technical Program Manager of Microsoft Research Asia. And today, let me introduce Agent Lightning, one learning system that makes all agents evolve. Our vision is straightforward. We want to build one system for every person and every organization to be able to evolve their own agents using their unique experience data. And for individuals, this means agents that genuinely understand your preferences, your needs through continuous learning. And for enterprises, that means distilling your specific workflows, your customers, your edge cases into an intelligence layer. And that can be a compounding mode that competitors cannot replicate. Agents exist on a wide spectrum. They vary in domains, implementation approaches, complexity, and more. While they all generate experience data, turning that data into improvement can be extremely difficult. That's why at Microsoft Research, we open source Agent Lightning to solve this. It connects any agent with any optimization method, making learning from experience practical with almost no code change. We achieve this compatibility by going back to first principles, specifically Reinforcement Learning 101. Every RL setup can be formulated as a partially observable Markov decision process, or you can call it a POMDP. In a POMDP, the RL agent takes actions, receives states and rewards from the RL environment without knowing all the details about how the RL environment works. And that is exactly how Agent Lightning goes. It abstracts such a POMDP from all AI executions. It treats only the part that needs to learn as an RL agent. Everything else becomes the RL environment. This design hides all the differences between AI agents inside the RL environment. So it is possible to optimize any agent using any learning method. And there are 3 key benefits. 1, a unified data pipeline that captures all agent activities using observability tools. It is non-intrusive to the original agent code. 2, algorithm flexibility that allows teams to plug in different methods without rebuilding everything. They can choose from classical RL algorithms to novel methods that are tailored for agents. This is important because the field is changing very fast, and best approaches varies by use case. 3, and finally, infrastructure disaggregation that separates agents and optimizes cleanly, providing modular components and a clear interface, allowing independent scaling of each part as you need. Here are some use cases from us and from the community showing how diverse the applications are. Let's start with the classic, a multi-agent customer service setting. So for this task, we use Agent Lightning to train a very small model. In just 8 epochs, the agent with a 1.5B model achieves comparable performance to an agent using GPT-4 series. And we also enable a new algorithm called EMPO². It is the first RL algorithm that can train agents with memory. That significantly improves exploration with new out-of-distribution environments. And optimization is not limited to model parameters. One team at Microsoft is building a specialized coding agent for writing formal verification in Rust. And with Agent Lightning's prompt tuning at less than $6 per task, they improved the average success rate by over 10 points. And multimodal robotic agents also use Agent Lightning to automatically tune their prompts. This improves the reasoning action coordination, doubling task success rate, and significantly reduce completion time. The community response has been extraordinary. Since open sourcing 6 months ago, Agent Lightning has earned more than 14,000 GitHub stars, ranking among Microsoft's top 50 most starred projects. It was featured as the #1 trending project on GitHub and the trending research paper on Hugging Face. This work reflects what we aspire to do at Microsoft Research. We tackle hard, fundamental problems, build open tools that serve the community, and push the frontier of what's possible. Our goal remains simple: build one learning system that makes all agents evolve, empowering every person and every organization to build intelligence that are truly their own. Agent Lightning is fully open source, so we welcome you to try it, contribute, and help shape what comes next. That's all I'm going to talk today. Thank you.
That was really great, Luna. It's always exciting to see research move quickly from idea to something that the community runs with. Next, we're switching gears to a problem many of us know well: translating messy, real-world ideas into something machines can understand. Optimization problems usually start in plain language: notes, constraints, and ideas written by humans. Turning those into clean, solver-ready math is often the hardest part. I have the pleasure of working with closely our next speaker, Shinchi, a research intern at MSR Redmond and a PhD student at the University of Washington. She'll introduce OptiMind, a specialized language model designed to close that gap by translating natural language problem descriptions directly into formal optimization models. This work pushes the state of the art in AI reasoning while also improving reliability in systems where correctness really matters. Let's dive into the details and new capabilities of OptiMind.
Hi everyone, I'm Xingzhi, a research intern in the machine learning and optimization group here at Microsoft Research and a PhD student at the University of Washington. Optimization is the engine behind the world's most critical systems, from global supply chains to logistics planning and vehicle routing. Today, I want to introduce OptiMind, which is our new 20 billion parameter reasoning model designed to translate natural language problems into a mixed integer linear programming formulations and a corresponding solver code. Essentially, it acts like an operations research expert to solve complex tasks in real life. In this project, which was a collaboration with the amazing MLO team here at Microsoft Research, we made two core contributions. First, we developed a way to clean up incredibly noisy optimization data using the expert knowledge. And second, we trained a small model that matches the frontier level performance. The task of OptiMind works as follows. A user describes in natural language a problem that involves some decisions that should be optimized. For example, please provide me an optimal production plan to maximize the profit across 6 months, given the specific capacity constraints. And the role of the language model is to generate the mathematical formulation corresponding to the problem and in the form of an executable solver code so that the user could run and get an optimal solution. And when we inspect the existing datasets and benchmarks in this domain, we found severe data quality issues. This applies to both the training dataset and the benchmarks used for testing. And in fact, we saw some training sets with up to 50% of the problematic instances, which include missing constraints, ambiguous descriptions, or wrong solutions. While we could manually clean the test benchmarks to ensure rigorous evaluations, fixing the massive training set is much more difficult. Training on the dirty data was like teaching a student with a textbook full of mistakes. So the first research question became, with such noisy data, how can we still train a competitive and reliable model? To solve this, we started by analyzing how models fail when answering the training questions. We noticed that within specific optimization classes, models make the same structural mistakes repeatedly. Take the traveling salesman problem as an example. Models consistently mishandle the subtool elimination constraints. Specifically, they often incorrectly apply the constraints to the starting node. And the result? This generates infeasible and disconnected loops instead of one continuous route. However, we found that if we add specific hints that could explicitly instruct the model how to handle the starting node, it will fix the logic. The model will follow the hints and generate a correct and feasible formulation. And this gave us a key insight. We don't need to manually fix every data point, and instead, our experts can identify these failure modes and write a library of expert hints. And think of the hint as a guardrail. Simple instructions like enforcing flow conservation or setting the big M number as the maximum variable instead of a fixed number will warn the model about these specific pitfalls before it even starts generating the solution. So we utilize the hints in two workflows. First, for data cleaning. We first classify the noisy training data and pair it with the specific hint. We then feed this to a teacher model, which uses the hint to reason correctly and regenerate a clean solution. And finally, apply majority voting to ensure robustness. This uses a rigorous and expert quality dataset with minimum human intervention. We then use this clean data to supervise fine-tune our base model, which is GPT-OSS 20 billion. And crucially, we repeat this pipeline at inference time. When the user query comes in, we first classify the problem type by identifying it, for example, as a traveling salesman problem. We then retrieve the specific expert hint and feed it with both the user's question and the hint into our model to solve the problem. And if the compute budget allows, we go a step further. We utilize the error messages from the solver to perform the multi-turn self-correction, ensuring the final code is executable and valid. So our results are very compelling. On the clean benchmarks, Industry OR Memo Complex and OptMass, OptiMind consistently outperformed the other open source reasoning models under 32 billion parameters by at least 10%. And when we compare against frontier models like GPT-5 and O4 Mini, we see that with just 5 turns of cell correction, we match their performance and sometimes even outperform them. And remember, we're achieving this frontier-level performance with only 20 billion parameters. The small scale of a model is also critical for local deployment. It allows organizations to keep sensitive supply chain data privately on their own GPUs, and it makes the research reproducible and accessible for the community. So to summarize, we proved that you can train a competitive domain-specific model starting from the noisy data by first distilling expert knowledge into reusable hints. And we believe that applying optimization in industrial practice should be a community effort. So we have open sourced our model, the clean benchmarks, and our examples of expert hints, so the others can build on top of OptiMind. And looking ahead, we're also working on fully automated pipelines using frontier models, so this approach can easily adapt to new areas, such as cloud efficiency, calendar scheduling, urban planning, and more. While we focus on standard optimization families, we hope the community will use our methods to explore new and less standard optimization domains. So I would like to thank all of you for tuning into this talk. Here are some resources if you're interested to learn more about this project and start using the models.
Work like this really highlights how much value there is in making AI systems not just smarter, but more dependable. That focus on trust and responsibility becomes even more important when AI is used in areas like healthcare. In many parts of the world, access to healthcare isn't limited by technology. It is limited by access to human expertise. Mohit Jain from MSR India will share HealthBots with Expert in the Loop, systems that combine LLM-generated responses with fast expert review. Deployed through familiar tools like WhatsApp, these systems are already helping patients and frontline healthcare workers get timely, trusted guidance at scale. This is a great example of research advancing AI for all, using AI to extend human expertise, not replace it. Mohit, over to you.
Hey, hi everyone. I'm Mohit Jain. I'm a principal researcher at the Microsoft Research Labs in India. Today, I'll be talking about the lessons that I learned while deploying HealthBots with experts in the loop. Let's get started. So patients, typically those who are undergoing critical treatment, let's say a surgery or cancer treatment, require timely, trustworthy and precise medical information. However, in a country like India, with only 7 doctors for every 10,000 people, it is very hard for a medical professional to spend a lot of time with every patient, which negatively impacts their information sharing with these patients. From a doctor's perspective, questions are fairly similar across patients. For example, if somebody who is undergoing a cataract surgery or who is going a head and neck cancer treatment might ask, when can I start eating biryani after surgery, or when can I drive my car again? With the advent of large language models, we somehow assume that it will help us make healthcare more accessible. However, as we all know, they do make errors and they do hallucinate. And because of that, even organizations like OpenAI and Anthropic clearly state that in their usage policy that for critical settings like healthcare, finance, or legal, we should not completely rely on large language models. So the main research question that we're trying to answer in this work was that, can experts, in this case medical professionals, help us improve the current AI systems? And in return, can AI systems help these medical professionals to attend more and more patients? So to answer these research questions, we developed multiple chatbots. One is for patients who are undergoing cataract surgery at an eye hospital. So let's see how it actually works in action. So in this case, the chatbot completely runs on WhatsApp so that there is no requirement to download a new software. Okay, and also it is most accessible in a country like India. The patient can ask a question in any of the languages that they are comfortable in, and they can even send a voice message. So in this case, they could have easily asked the same question by sending a voice message in Hindi. Here, for the sake of the broader audience, let's say the patient asked this question in English: when can I wash my hair after the cataract surgery? We use a knowledge base that has been curated by the doctors of that eye hospital to generate this answer, which states you can wash your hair 3 days after the surgery. However, it comes with a question mark because the answer has still not been verified or vetted by a doctor. We also generate a few related questions so that the patient can continue this conversation. At the same time, when this answer comes to the patient, the answer is also sent to the doctor who is going to operate on that patient. And along with the question answer pair, the doctor also receives this simple question: was the bot's answer correct and complete? And the doctor has 3 options. They can say yes, this is a correct answer. They can say no. Or they can even delegate the question to a patient coordinator to answer it. Because we are doing some kind of classification in the backend, whether it's a medical question, then it goes to a doctor. If it's a logistical question, it goes to a patient coordinator. Let's say in this case, the doctor says that the answer is incomplete. So that triggers a longer workflow. So we inform the patient upfront that the previously provided answer was invalid and please wait for the corrected answer. Along with that, we ask the doctor, please reply with a correction. And here's the beauty of our solution. The doctor is not required to manually edit the answer. They have to just provide a feedback, which can be grammatically incorrect, which can be incomplete, it's completely informal. In this case, the doctor could have just written 2 followed with a space and WKS, and we would have got it that the doctor is saying that they have to wait for 2 weeks and not 3 days. However, that answer is not sent to the patient. The patient receives a more formal version of the answer saying that better to avoid washing your hair for 2 weeks after the surgery. And it also comes with a green tick mark and with the statement that this is a verified answer by your doctor. Now we have this really important data from a medical expert. So we use that data to update the knowledge base so that the next time if another patient asks a similar question, let's say a different patient asks this question, surgery is done, can I shampoo? Which is pretty much the same question but in a different way. So we informed the patient that previously answer was provided to a similar question, and does this answer your question, yes or no? So this pre-verified answer reduces the expert's workload over a period of time. Now this system has evolved into a broader framework, and we call that Build Your Own Expert Bot, which is available as an open source tool on Microsoft GitHub page. So anybody can build these expert in the loop chatbot. We use the same platform to build 3 of these deployments. One, as I told you about, for patients who are undergoing cataract surgery at the Sankara Eye Hospital. This has been running at 3 hospitals of Sankara Eye in Bangalore, Hyderabad and Jaipur, supporting different languages and different socio-economic demography of people. More than 3,000 patients have used it in the last 9 to 12 months, and more than 10,000 questions has been answered, and more than 20 doctors are actively verifying these answers. For community health workers, we have deployed it with an organization called as Khushi Baby. Right now, it is actively working in 5 different districts in Maharashtra and Rajasthan state of India. More than 11,000 ASHA workers, who are the community health workers in India, have used it. And more than 50,000 questions have been answered. In the community health worker scenario, the experts are not doctors. They are actually ASHA supervisors, who are the auxiliary nurse midwives. And hence, instead of a single doctor, in this case, a pool of these ASHA supervisors are the one who actually vet every answer. In case of the third deployment is for patients who are undergoing head and neck cancer surgery at the Kasturba Medical Hospital, and that system is called as OncoBot. So through all of these deployments, we have learned multiple lessons, and the most important ones I am putting it here. The first one is that expert verification. Whenever we say that your doctor, let's say Kaushik, has verified your answer, it actually adds a lot of trust to those answers. So it's very, very important for us to add this expert in the loop. And also we need to make sure that the workload on the doctor is minimal, and hence that all that shorthand, grammatically incorrect correction is what it needs to make the system work. Also, the system is completely asynchronous. The doctor doesn't have to respond in real time. They can respond whenever they are taking a coffee break or something else. Second is that compared to other kind of system where we really enjoy the creativity of a generative AI system, in our case, reliability beats that creativity, because a constrained static AI relying on the RAG pipeline actually outperform these fully Gen AI system, wherein we can't control for the kind of output it will generate. And that also acts as an automatic guardrail to the system. The third point is that admitting uncertainty. In our case, whenever the bot is unaware or is not sure of an answer, it just says, I don't know. Okay. For example, if a patient would have asked, like, what should I do in case, can I do pranayama after my surgery, which is a kind of a nasal yoga, but knowledge base doesn't have that information. So the bot will just respond saying that I don't know, and the answer will be then given by the doctor. The fourth is that localization is not translation. A typical Azure language technology translation works really well for certain languages, but for local Indic languages like Hindi or Tamil or Telugu, it doesn't work that well because it doesn't have the domain, culture, or the contextual knowledge. So hence, instead of that, we started relying on GPT because we can always provide that context that this is a question asked by a ASHA worker. For example, when ASHA worker asked about the side effects of Antara Tika, which is a kind of a contraceptive, the translation from the Azure language technology was Antarctica. Okay. However, when actually we give this information, this is the question asked by ASHA worker, we get the appropriate translation. And finally, in the current ecosystem, healthcare ecosystem of India, there is a huge power difference between a doctor and a patient, even between an ASHA supervisor and a community health worker. And they are always very hesitant to ask very dumb or simple or basic questions to them. However, because there is a chatbot which is sitting in between the two end users, and the chatbot is non-judgmental, and that actually makes the patient or the end user, like a community health worker, gives them more power to ask very fundamental or basic question without getting judged. That's all from me. Thank you.
That was inspiring, Mohit. It's exciting to see AI making a real difference while keeping people firmly in the loop. Next, let's look at a brand new research breakthrough that goes straight to the heart of how large AI models are trained. Training large language models efficiently is one of the biggest challenges in AI right now. From Microsoft Research Cambridge, Chao and Wembo introduced Adaptively Rotated Optimization, or ARROW, a new approach to optimization that uses geometry-aware updates to significantly improve training efficiency at scale. This is fresh work coming straight out of the lab, with timely results and big implications for both research and production systems. Handing it over to you, Chao and Wembo.
Hello everyone, my name is Chama and I'm a senior researcher at Microsoft Research Cambridge. We have been working on innovations in AI efficiency, and together with my colleague Wembo, we'll talk about ARROW, the new matrix optimization framework for large models. This has been a collaboration with an amazing team at MSR Cambridge. To begin with, training AI is expensive, and the optimizers crucially determine how effectively they turn compute into intelligence. The industry so far has been dominated by the use of Adam for a decade. Now, matrix-based optimizers like Dion are emerging using gradient orthogonalization methods to improve sample efficiency and supporting production-scale training. From our perspective, we believe orthogonalization as one example of this new optimization research landscape. And the goal of our work is to develop new paradigms in optimization that push the efficiency frontier even further. To explain our approach, let me start with the basics. Gradient descent is the simplest optimizer. It computes a gradient G and uses it to update the weight W. Adaptive optimizers like Adam also follows the gradient, but they adaptively rescale the gradient before applying the weight update. The adaptive rescaling is implemented by some nonlinear mapping, F. And more recent matrix optimizers like orthogonalization, shampoo, and soap, etc. are more complicated. However, despite very different motivations and derivations, they are fundamentally similar to Adam. After some simplifications, we can show that they run Adam-like optimization, but in a rotated coordinate system. Concretely, this happens by first rotating the gradient by R transpose, then apply the nonlinear map, F, in that rotated basis, and finally rotating back. In the literature of matrix optimization, F is typically variance of Adam, and R is chosen as the single vectors of G. This reinterpretation is not entirely new. But based on the insights from our research, we believe rotation should not just be a reinterpretation, but instead a core primitive principle for optimizer design. This perspective opens the door to many new ideas in optimization, and in particular, we propose the use of more powerful nonlinear mappings beyond Adams rescaling, and more significantly, better rotations that are informed by the choice of F and deliver improved sample efficiency. And that gives our framework adaptively rotated optimization, or ARO. Before going to the details of ARO's performance, let me first comment on why we believe rotations are so important. We hypothesize that it is really rooted in symmetries of loss landscape. Current language models architectures choices for sample transformers have rich rotational symmetries in their weights, which, when applied correctly, those rotations will leave the model's predictions unchanged. ARO exploits this property by moving along those symmetry orbits without changing the model's output to search for updates that are more effective at navigating the loss landscape. And this symmetry hypothesis also enables additional features of ARO, for example, leveraging cross-layer couplings for better performance. In summary, ARO is a general optimization framework that not only explains many existing matrix optimizers, but also enable the discovery of new update rules that work very well in practice. Now, I will hand over to Wenbo, who will walk through our key results.
Thanks, Chao, for introducing ARO. Hi, I'm Wenbo. Since we have covered the key features of ARO, next I will briefly talk about how it performs in practice. To ensure fair comparison, we have carefully built an optimizer benchmark protocol that aims to mitigate many potential forms of evaluation bias. First, we collaborated with Microsoft Research Asia and evaluated ARO on their newly developed MOE model called Sigma. We measured the optimizer performance using the relative speedup in steps over AdamW. This is shown in y-axis, and the x-axis indicates the data scale, where each unit represents the chinchilla compute optimal dataset sizes. For example, this spot indicates the 1.36 times speedup at the 8 overtrain factor. It means that ARO only uses about 73% of the data or GPU time to reach the same loss as AdamW at that training stage. Therefore, the higher the speedup, the more efficient the optimizer will be. From the plot, we can see the result forms two clusters. The lower cluster represents orthogonalization-based method, including mu1. The upper cluster shows two ARO variations. Their results shows a clear performance gain for ARO, which persists across data scales. Importantly, ARO can optionally be used as a full model optimizer, where all matrix parameters in the model are updated under a single rule. While some orthogonalization methods, although we do not show it here, can be unstable in that setting. Overall, this suggests ARO converges faster and delivers better sample efficiency under our rigorous benchmarking protocol. Next, we stress test ARO across model scales to check whether its efficiency gain holds as we scale up. We evaluate ARO on models from 0.3 billion up to 8 billion parameters, covering different architectures and overtraining regimes. This plot shows the speedup comparison of ARO versus mu1 and AdamW. From this, we observe that ARO remains consistent advantages around 1.3 and 1.1 times over AdamW and mu1, respectively. As model size increases, we do not see the advantage shrinking at larger scales. All of the experiments use our efficient distributed ARO implementation. In our setup of 8 billion runs, the per-step runtime is on par with AdamW, meaning that the speedup translates directly into walk clock time savings. Overall, these results suggest that ARO speedup is scale robust. Based on this trend, it is likely to maintain its advantages over AdamW and mu1 as we move on to even larger models. To summarize, ARO is a general framework for matrix optimizer. It not only unifies many existing ones, it also provides design opportunities for novel and more efficient optimizers. Additionally, Arrow can be easily extended and therefore incorporate new developments in the matrix optimizer community for further improvements. Our empirical verifications shows consistent advantages over both AdamW and Muon across different model and data skills. Overall, we believe Arrow is a competitive optimizer for training large model at scale. We want to thank all the collaborators in Microsoft Research and all interns for their valuable contributions, discussions, and feedback. If you are interested, please find the paper link in below.
Thanks, Chao and Wenbo. By the way, you can read the newly released Arrow paper with the link below. We'll close today's episode with another fresh idea from the lab that tackles efficiency from a different angle. Working out of the New York City lab in the AI Frontiers team, Quenjun is here to introduce Dion 2, a simple yet powerful method that makes advanced optimizers more scalable by shrinking the expensive computations they rely on. Dion 2 preserves performance while dramatically reducing cost, opening the door to faster and more flexible training at scale. It's a great example of how elegant, focused research can have massive impact on real-world AI systems. Let's hear more.
Hey, I'm Kwangjun. I'm here to talk about a new simple method to shrink matrix in Muon called Dion 2. Our work is in line with orthonormal optimizer revolution. For context, training AI models consume a lot of compute, and we want to do this better. The current de facto standard for training AI model is something called AdamW, and is extremely popular. And here the question is, can we do better than this default algorithm, AdamW? Recently, there is a new contender for AdamW called Muon, which is the orthonormal optimizer. It is an optimizer for matrix parameters, which make up nearly all parameters in modern neural networks. The key idea here is to orthonormalize each update matrix. It has clean theoretical motivation and strong empirical performance. In particular, it has been adopted in frontier models such as Kimi and GLM. So should we all switch to Muon? Not so fast, because it turns out it's a bit tricky to scale Muon to larger scales. It's mostly because Muon relies on matrix-level computations, which conflicts with distributed training where weights are sharded. And inherently, the Muon computation, specifically orthonormalization, is superlinear complexity computation. This is in contrast with AdamW, which only relies on element-wise operations. Hence, it's scalable and compatible with all the distributed training framework. So here's our idea. Can we add a scalability knob to Muon to make it more scalable? What I mean by that is, let's add a parameter controlling how much of the update matrix we're orthonormalizing. Let's call it beta, which is in between 0 and 1. When beta is chosen to be 1.0, it recovers the original Muon, hence orthonormalizing the full matrix. Whereas when beta is chosen strictly less than 1.0, we're doing partial orthonormalization, hence leading to cheaper compute and less communication, and hopefully it retains all the benefits of Muon. So scalability knob, again, is chosen between 0 and 1. And the goal here is to, when the beta scalability factor is chosen strictly less than 1, it still preserves strong update quality benefits of Muon, even with the orthonormalizing only a fraction of the matrix. That's where Dion 2 comes in. It's a very simple method to shrink matrix size in Muon. And here is the outline of our results. On the left-hand side, we're showing optimizer step benchmark between muon and Dion 2 with various fractions. And you can see that as fraction beta becomes smaller, Dion 2 achieves speed up over muon. And on the right-hand side, we're showing the training runs between muon and Dion 2. And even with the 25% of orthonormalization, Dion 2 is achieving very competitive update quality as muon. The remarkable thing about Dion 2, which makes it practical, is its simplicity. It first picks top beta fraction of rows or neurons based on their norms. And then we orthonormalize only the chosen rows or neurons and decay them, the selected rows, so that various diverse neurons get selected across different training steps. This is in contrast with Dion 1, which relied on somewhat complicated low-rank approximation for efficiency, and its reliance on linear algebraic function comes with overhead at small scale, which makes it less practical. Also, in our experience, Dion 2 achieves better update quality than Dion 1, making it better and more practical optimizer than Dion 1. Please try out Dion 2 in your code base. You can use the same configuration as muon as long as muon is integrated in your code base. In our experience, beta equal to 0.5 or 0.25 leads to a very competitive algorithm with full muon. This is our experience while integrating our Dion 2 and muon to Phi code base. And you can see that Dion with 0.5 or 0.25 achieves very competitive update quality. In other words, once muon is in your code base, Dion 2 is plug and play. Here are some references. You can check out Dion 2 implementation from our Microsoft/Dion code base, and you can check out more details about Dion 2 from our paper. Thank you for listening.
And that brings us to the end of today's Microsoft Research Forum. A huge thank you to all our speakers for sharing such a wide range of work, from early exploratory research to open source systems, mission-driven AI, and brand new tools. Today, these talks capture what makes Microsoft Research special: deep curiosity, collaboration across labs and disciplines, and a focus on turning ideas into impact. You can watch all of today's talks on demand and explore papers, open source repos, and all resources on our site. Make sure to register for the series to hear what's new from MSR. You can also hear from our Microsoft Research CVP, Doug Berger, in his new podcast series, The Shape of Things to Come, where Doug talks to experts from different fields about how AI works, open research challenges, and opportunities to shape the future. Thanks for joining us, and we'll see you at the next Microsoft Research Forum episode.
Thank you.